right? Okay, the ninth property, the last property of multivariate normal, distribution. Let x1, x2, another kind of two vectors, right? X within parenthesis 1 and within parenthesis 2. So when you have like this, you know that this is not simply two responses x1, x2, right? These are like set of responses. X1 is a set of responses and x2 is also a set of responses. That's why those are vectors. Can be set or just a single one, doesn't matter. The property is true even it's a single value, simple x1 and x2, right? Be distributed as p-variate normal with mu and sigma with mean vector and variance covariance matrix again partitioned. And we have a special property here, determinant of sigma 2 is positive, right? Then the conditional distribution of x1 given x2, which is x2. x2 is given, the second part is given, it's given as simple x2. So it has a multivariate normal distribution. That means here we are saying something like this. x1 given x2 distribution. The given value is given as x2. That has another multivariate normal distribution with, we'll say, mu star and sigma star, variance covariances. So this is that mu star and this is the sigma star, right? Mu star equals mu1, that means the mean of the first column, first part, right? So conditional distribution, you know the meaning, right? Conditional distribution is actually we are finding the distribution of x1 with a condition given x2 values. So what's the number here? I didn't ask, this is not univariate normal. So whatever the dimension of x1, right? Suppose x1 is q by 1. Suppose x1 is q by 1 and x2 is p minus q by 1 because x we consider as p by 1. So then this should be nq because x1 is q by 1, right? We are finding the distribution of x1 with some conditions, with the condition. So it's q by 1 vector x1. So it's q variate normal with given mean and variance. You can see the mean value is mu1 plus mu1 is the mean of x1 part, right? Plus sigma 1 to 2 inverse x2 minus mu2. x2 is the given value, mu2 is the mean of that. And the variance, sigma star, which is sigma 1, 1, that's again the variance covariance part of x1 term minus sigma 1, 2, sigma 2, 2 inverse, sigma 2, 1. Right? You have to remember these two, or you have to memorize these two formulas, mean and variance of conditional distribution. This is actually something you are already familiar with. I don't know how much you are familiar with that one. So conditional distribution. So in univariate, you always did individual variable, right? But when you started doing regression, you fitted the models for y to find the value of y for given values of x, right? So that if I consider simple linear regression equation, so you write y hat equals beta naught hat plus beta 1 hat x, x, we'll just say x, right? So using the regression equation for given values of x, we find y, right? That's our objective. Find the values for given values of x. So this is actually, if you write y given x, that's again same thing, right? Y hat for given values of x. That's our regression equation. Okay, so If you write like that, so what's the mean? What's the expected value of y hat here? So expected value of beta naught. What's the expected value of beta naught? Beta naught hat, sorry. So without writing expected value, if we write expected value, it comes to beta naught, the parameter directly. I just asked, what's beta naught in simple linear regression? Regression kalane. ඔය රසිකා කියන්න තියවා කරනකොට මම අහයි කියලා. Yes, Nadeem. That's the intercept. I'm asking the equation. Beta naught equals in terms of x's, y's, those things I'm asking. Simple linear regression. මතක නැද්ද? Beta naught and beta 1 එන්නේ කොහොමද කියලා? Yes, Tarushi. Yes, beta naught hat equals y bar minus beta 1 hat x bar, right? Y bar minus beta 1 hat x bar. So plus beta 1 at x. So if you take y bar minus, not minus, we'll take plus beta 1 at x minus x bar, right? So y bar plus beta 1 hat that terms of x, sx, xx, xy likewise you had, right? Beta 1 hat, usually beta 1 hat equals summation xi minus x bar, yi minus y bar over sum xi minus x bar square, right? Yes, Pavanti, yes, Tarushi. It's sxy over sxx. X minus x bar. That's exactly this equation for mean here, right? If you look at this one, now here we had y given x, right? Now in terms of y, we have x1 given x means x2, which is simple x2, right? We don't need the parentheses here. That's a given value. That means a number. Right? So we have y bar. Y bar means in terms of y, now we have x1. So it's x1 bar, something like that. Plus sxy over sxx. In terms of x, we have x2 now. Given value is x2 now. So x2 minus x2 bar. Right? So that's it, the same thing. Here we have mu1, mean of x1. So that's the x1 bar, right? Plus sxy over sxx. So sxy is the sigma 1, 2 part, right? Not exactly that. We are talking about the vector version of this one, right? But this is our usual univariate one. So sxy, the multivariate version is sigma 1, 2. We divide by sxx. Yeah, I had to change these x's and y's also. So sxx means x is x2. So that's why we have sigma 2 to inverse. That sxx part comes up as the inverse. Then x2, that means the given value, minus mean of second given variable mu2, right? So it's exactly the same form in our simple linear regression. When the x values are given, how to find y values, right? The variance formula, again similar, you can get it from something you learned in your first year or second year. I'm not so sure whether you remember, probably you have done, right? A variance value, when we have conditional variance, we can write it as, if you remember, variance of expected value of y given x plus expected value of variance y given x. Do you remember something like this that you learned? With the conditional expectation and variances. Yes or no, at least. I think first year you may have it. You can check, right? So here also you can see, here we are finding variance of this term. That's our sigma star there. Variance of expected value of y given x, right? That's our sigma star here. So it would be variance of y, which is sigma 1, 1 minus this part. So that's the part comes as this. Sigma 1, 2, sigma 2, 2 inverse, sigma 2, 1. You can show it. I mean, it's in the same form, right? I'm not going to show it. Probably you'll be confused now. So we look at this example. So anyway, what you have to do is, when a conditional distribution has to be found by giving the original distribution of x's, you can use this mean and variance, right? So here's the example. We look at the example. Okay, find the conditional distribution of now this is the original distribution I have given. You have let x's. So it's again 3 by 1 vector x, x1, x2, x3. Those are the components, right? You have to find the mean x1 or distribution. First, the first one. Right. You have to find the mean and variance. So this x1, or simply writing x1, x2 given x2, x3 equals to that distribution you have to find. You know that it's normal. You have to find mean vector and variance covariance matrix. The main thing is you have to pick the values correctly. So before going there, I'm asking, what would be the number here? So here I said we are finding the distribution of x1 with some condition. x1 means x1 vector, right? X within parentheses 1 vector. So we are actually finding the distribution of this x1, x within parentheses 1, with a condition that x2, the rest of it is given, right? So as I said, it should be the dimension matches with the one we are going to find the distribution. Yes, Pavanti, correct. So it should be 2, right? Because we are really finding the distribution of x1, x2. So this is my x1. This is my x2. X2 is not a vector now, right? Just a single value. Yes, Tarushi. Okay, now you have to find mu star and sigma star. So mu star mu star equals mu1 plus sigma 1 to sigma 2 to inverse x2 minus mu2. Right? Now, what's mu1? Mean of what we have to find the distribution. x1, x2. So you know that from partitioning, here's the place you have to partition because it's x1, x2 versus x3. So that's what you have to get. Now you should know this part is mu1. This part is mu2. Right? And this is your sigma 1, 1. This is your sigma 1, 2. This is sigma 2, 1. This is sigma 2, 2. That's the thing you have to figure out correctly. Right? We are finding the distribution of x1, x2 given x3. So x1 part, x2 part, you have to find the variances, means and variances separately. And once you figure that out, it's just plugging and doing some calculations, nothing much, right? So mu1 part is minus 1, 2. Sigma 1, 2. Sigma 1, 2 is 0, 0. Sigma 2, 2 is 4. So sigma 2, 2 inverse 1 over 4. x2 is the given value, which is 2 here. Mu2 is 1. So the second part you have 0, 0. That means multiplication 0. So the answer is minus 1, 2. Same way, sigma star, can you find? First tell me, do you have any question with mu star? Did you understand how to get this mu1, mu2, sigma 1, 1, sigma 1, 2 likewise? All the previous properties also come into play here because we are going to use these partitions and get the distribution separately. So we want to find the distribution of x1, x2 given x3. So we have to have x1, x2 distribution. We have to have x2, x3 distribution separately and the covariance between the two also. So that's how my mu1, mu within bracket 1 is the mean part of x1, x2. So minus 1, 2 likewise. So what sigma star? You can keep calculating. Sigma star. So sigma star, the equation, you don't have it, right? This one, sigma 1, 1 minus sigma 1, 2. I'll write it here. Sigma 1, 1. That means variance covariance part of x1. 2, minus 1, minus 1, 3. Minus sigma 1, 2. 0, 0. Sigma 2, 2 inverse. Sigma 2, 1. Check whether the dimensions are correct when you take, right? This is a 2 by 2 matrix. So sigma 1, 2 is 2 by 1. 2, 2 inverse 1 by 1. 2, 1, 2, sorry, 1 by 2. So you end up with 2 by 2 part there also. But you have 0, 0 parts in the second one. So you can get 2, minus 1, minus 1, 3. So this conditional distribution is a bivariate one with negative 1, 2. That's the mean vector, and variance covariance matrix 2, minus 1, minus 1, 3. Any question here? That's the conditional distribution. And you can see now the conditional distribution of x1, x2 given x3 is same as distribution of x1, x2, right? Because mean is this part, variance covariance is this part. Why? Why did that happen? That x1, x2 given x3 distribution is same as, the distribution of x1, x2. Yes, Ashoka, exactly. x1, x2 given x3 distribution is same as x1, x2 distribution. The reason is these two are independent, right? You can clearly see that from the matrix, right? So once you partition x1, 2 with x3, x1, 2 distribution is independent of x3, right? Because sigma 1, 2 part is 0. Property number 5. So x1, x2 is independent of x3. So for the distribution of x1, x2, x3 does not matter, right? Because the two are independent. So conditional distribution is same as the marginal distribution. That's why we have mu star and sigma star directly x1, x2 values. Actually, without plugging in all this, you could have just say those two are independent. So x1, x2 distribution is directly, sorry, x1, x2 distribution given x3 is same as x1, x2 distribution. Right. Any question here? If so, can you find the next one? x1, x2, x1 given x2, x3. So x2, x3 is given. Now you have to partition accordingly. Right. So x1 and x2, x3. So you have to partition from here. x1 and x2, x3 like this. So this is going to be your mu1. This is your mu2. And this is your sigma 1, 1. This is your sigma 1, 2. This is your sigma 2, 1. This is sigma 2, 2. Right. So using those, you have to plug in here. So we know that this is a normal distribution with another mu star. We'll say mu 2 stars, sigma 2 stars. Okay. I'm asking a question again. What's the number of variates here? What's the number comes here? Just say one thing. So we are finding x1 given x2, x3 distribution. So Tarushi, yes. Himasha, yes. Others? Oh, me neither. 19 students, great. Maybe I'll just post the complete notes and ask you to just go through and learn. So what's the point of having a lecture if students don't want to come, right? I don't have to blame you because you all are here, but that's what has happened here, right? Yes, Pavanti, correct. Yes, Nirasha, correct. Yes, it's a univariate distribution, right? It should be 1. That means it's univariate distribution. Yes, Kasumi. So it's univariate distribution. That means you don't even have to write it. Okay. Now you have to find mu star and sigma star. Can you do? Mu star, mu double star. So mu1 plus likewise. Okay, that part homework. Find mu double star and sigma double star and find this distribution. What's the x1 given x2, x3 distribution? You have to pick the values correctly, values of vectors correctly and plug in and simplify, right? It's going to be a univariate distribution. So remember mu star, mu double star is a single value, sigma double star is also a single value, right? Okay, so that's the homework and you can do it and see you next time if there are no questions. We have a few minutes actually, 12:21, 4 more minutes. So if you have anything, you can ask. Any questions? Nothing? Okay, then we'll wind up then. Hope to see you next time. I don't know whether lower numbers, but what can I do? So last time also I said, if you have suggestions or something, you can say, but I didn't hear anything. So I assume that those who need the lecture, they will come for the lecture. Others, I don't know. They will follow the video recording or whatever. I don't mind. But anyway, remember, without participating in the lecture, it's hard to get a good grade, right? Because I'm not going to give you straightforward questions, not for the exam. Okay, so see you next time. Have a good week and have a good holiday tomorrow and day after. Okay, see you then.
Thank you, madam.
You're welcome.
Thank you, madam.
You're welcome.